Good morning, good afternoon, and good evening. Welcome to another episode with us from CIQ. We appreciate you spending the time with us today. So today we're going to talk more about Fuzzball and about workflows. And Forrest has spent a lot of time coming up with some great examples and some great use cases and topics for us to talk about today. So we're going to have Forrest and Michael and Greg join us. Welcome, fellas.
Hello, everyone.
Again,
Hello.
Michael, good to see you.
Same here.
Greg, as always. So, Forrest, I know you put in a lot of time over the last few days to kind of put together another set of really good examples of what Fuzzball can do, what use cases we're kind of seeing and people are asking a lot of questions about. So why don't you go ahead and tell us what we're going to see today?
Awesome. Well, hello, everyone. Thank you all for joining. Today, we have a couple of different workflows that we're going to be showing off, a few, actually. The first one is QMCPACK, which is, if I can find my notes to make sure I don't biff it, but I don't think I have them. QMCPACK is a piece of software that people use for doing what are called Quantum Monte Carlo computations. So very low-level quantum interactions, different types of very specific simulations. It's a pretty fully featured suite. It's got a lot of different things you can do with it. So we'll be taking a look at that. We also have Quantum ESPRESSO queued up, which is what's called essentially like a quantum dynamics software that's used for very nanoscale materials modeling, nanoscale electrical calculations, that type of stuff. So both of those workflows are kind of more focused on the extremely small scale. And then we also are going to be taking a look at kind of just a random example of using what we call a task array in Fuzzball, which allows for embarrassingly parallel runs to be done. And we'll kind of be taking a look at that in the context of something that you could view as maybe like a quantitative finance example or something like that. So without further ado, I will go ahead and start off QMCPACK, and I'll kind of go through the, what we're looking at there. I'll go ahead and, like I mentioned, start it first. So let me share my screen really quickly.
But one thing, Forrest, let me remind everyone, for those of you guys who are watching, feel free to ask questions. Let's keep it live and interactive. Whatever you have, just throw it in the chat. We'll address that. But I also want to point out that Forrest is doing this live. So it's always fun and exciting to do live demos.
Yes, it is indeed. Let's see here. All right, can everyone see my screen all right? Okay, there we go. I'm not sure if I can make that text bigger, but we'll roll with it. So as you can see, I'm here on my just VS Code terminal. That's where we're going to take a look at the YAML definition that's going to power this QMCPACK 1. I'm actually, now that I think about it, just one moment, because this takes a couple of minutes, and just to make sure we don't run out of time in the meantime, we're actually going to go ahead and start this off to begin. So you can see I'm here in the command line. We're just going to do a quick Fuzzball workflow start, and then we'll just provide a name for it. So we're going to call it users fbert@ciq.co, QMCPACK demo. And then we just provide the path to where that's at. So that's in QD, or where that workflow definition that I'm about to go over is at. So we'll just do this. .yaml, there we go. Okay, perfect. So we've just gone ahead and started that workflow. I'm going to put its status up here so we can monitor it, kind of switch back and forth. You'll see we have a few different things going on here. I will explain everything. So let's switch back over really quickly to that VS Code window that I was on, and we'll kind of run through what everything is doing there. So this QMCPACK workflow has a few different jobs in it, and also has a few images, a few volumes. It's a little bit, it kind of uses more than just one of those things, like maybe we've shown in some of our past demos. So just beginning up here at the top of this QMCPACK workflow, the first thing that we're doing is creating two different volumes. We're creating one for some data to be ingressed into, and then we're creating some data to be egressed out of. This is more done just for demonstration purposes. There's no specific need to create an entire directory just to do an ingress or do an egress. You can do it with one just as easily. But just to kind of illustrate moving data around between volumes and that type of thing, I chose to do this with two. You can see that I'm basically just reaching out to an S3 bucket on AWS in this case. I'm going to pull down this file for QMCPACK to use from that bucket. And then we're going to place it into this first volume, QMCPACK data, at this location. This is an ephemeral volume, meaning both of these are ephemeral volumes, meaning that they only exist for the lifetime of the workflow. So this data will be ingressed. The jobs will be able to operate on it in a persistent manner relative to other jobs. And then once the egress here is done, the ephemeral volume will essentially be dropped on the floor and the data in it lost. So anything not egressed will be lost there. So like I said, we have 2 volumes. We'll move to the jobs now. We have 1, 2, 3, 4 jobs in this case. The first one is just an untar. This is basically just untarring this tar GZ that we ingressed in this first step. So we're just mounting that data volume that we ingressed into with this mounts field here to this location inside of the container. As we've noted, in Fuzzball, everything is a container. All these workflow jobs that this computational workflow is going to be doing are run out of a specific container. In this case, because we have not really any other need for specific tooling, we're just using a small Alpin container being pulled from the Docker Hub to provide tar in this case for this initial untar job. The next job up here is, and you can see that we have 8 cores requested, 30 GB of memory, and the command is basically just a tar command. So this is basically just spinning up a standard CPU compute node to just do an untar on. We then have the run QMCPACK step, which is a little bit more complex. You can see that the image we're using is something that we're pulling from NVIDIA's NGC. So this is something that they've put together to run this on. This is something that they've put together to run, especially on GPUs. So you can see that in this case, as far as GPUs go, we're requesting 1 of them. We're also requesting 4 cores and 60 GB of memory. This is going to match more or less the definition that I've set up that'll pull us down a node off this public cloud provider that'll have 1 NVIDIA V100 GPU in it. And because down here with this MPI field, we're requesting 4 nodes with an OpenMPI implementation of our MPI wrapper. You can see that we'll actually end up getting 4 of those compute nodes. So we'll have 4 V100s in total, with our MPI wrapper managing parallelizing that over all those nodes. So this will run. This step takes 15 to 20 minutes or so to run through all of that. We have an environmental variable here that we're setting just to make sure that we're using the right process management library relative to OpenMPI. And then you can see the command we're actually running here is basically just QMCPACK based on some input data. You'll notice that we're mounting the QMCPACK directory to this host PWD directory inside of the container. And then we're also saying that to be our current working directory. We've done that because we untarred in this step all that data into that host PWD directory. And so in this case, we just need to specify our working directory and then what file in there we're going to be feeding into QMCPACK. The next couple jobs are pretty simple. One is just an LS, so we can have some visibility into what data was produced from this run once it's done. There's nothing too special there. It's once again just Alpine, just doing an LS LATRH there. And then it requires, you can see with these requires things that we're building up a directed acyclic graph of execution here. And we do that because obviously the data has to be untarred, the simulation has to be run. And so we have a path of execution that we're trying to follow here. And so this ls command, or this ls job here, it's basically just going to show us what's in that host PWD directory. And then our last job is tar outputs, a volume egress directory, and that I think I must have copied that over and forgot to switch that. There shouldn't be a problem there. It should be just fine, but that is not the container I meant to use there. It should be fine otherwise. Yeah, it should be fine. It's just doing a tar command, so we could do something just as minimal as alpin there, and it would be fine. But as we'll get to notice, we've got now 3 different containers being orchestrated and pulled from somewhere and managed for this workflow. So that's kind of a neat aside there. So you can see this tar outputs job. Like I said, it's just going to use just something very minimal to tar up what's in host PWD and place that into egress. And then once this job is done, the workflow itself will complete. We'll go back down here to the bottom at this egress, and this file, which we tarred up in that step, just to point out, whoops, my heavens. accidentally pasted a bunch of stuff. You can see that this is the directory that we've created, that tarball there. And then you can see that we're going to egress that same directory up to this S3 bucket right there. So let me just tab into the other screen and see how this is working. Looks like it is, in fact. Let me switch over real quick. So I'll show you guys this running, and then we might get into a couple of the other ones, because like I said, this will take about 20 minutes or so. So just moving back over to this really quickly, you can see that we've been watching this status output here. Just to map what we've just seen in that workflow to what we're seeing here in our status output. We have all these lines here along the left. Each one of these represents a different part of this workflow. You see that we have workflow up here at the top. That's just kind of delineating the workflow as a whole. It's kind of just representing the time that overall that it was started and stopped, or started and finished, and then its name, basically. We have the two volumes that we set up right here. Those finish basically instantly. Those are just setting up that QMCPACK data and egress directory that we're going to be using to store some data for these jobs. So those are those two volumes being set up. We then have the two file transfers. One of them says finished, one of them says pending. You'll notice this one shows something moving in from S3. You'll notice this one shows something moving out of the cluster and onto S3. So this one is finished because this represents our data ingress that we showed there. This one is pending because it represents the data egress that won't happen until all these jobs are finished. We have these images here that have been downloaded as well. Each one of these image lines is a container that has been downloaded for this workflow to use. As I mentioned, we're using Alpin to provide just kind of basic tar stuff. We're using QMCPACK for QMCPACK. And then apparently we're also using Quantum ESPRESSO for tar as well. But as mentioned, ignore that, just a typo. So you can see that we then have the four jobs here: untar, run QMCPACK, ls, tar outputs. You can see untar is finished, and it got done about 3 minutes or so ago. So right now, tar outputs, or not tar outputs, sorry. Right now, run QMCPACK will be spooling. And I'm just going to...
Forrest, I may be jumping ahead a little bit, but the egress on that can be to anything. It doesn't matter. It doesn't have to be S3. It can be to whatever storage you want it to go to, right?
I mostly use it in the context of S3. If we had set up as a persistent volume, we'd be able to perhaps move it out into a physical architecture. But at the moment, I mostly use that to push to S3. You'll notice that in that workflow I had there, I have some very specific parameters that I've set. Let's see here, where is it at? You'll notice here that I've set a few different parameters: S3 access key ID, S3 access key, and S3 region. Those right there.
Sorry.
Oh my heavens, sorry everyone. Let's see here. Is that better?
There we go.
Okay, cool. So you'll notice that down here in the secret section of this, this egress, and for that matter, the ingress, we have S3 access key ID, S3 access, S3 access key ID, S3 access key, and S3 region. These allow you to specify basically just standard S3 API compliant credentials that allow you to reach out to any S3 compliant API object storage out there. So some places, the S3 API isn't just provided by Amazon S3. It's also provided by some other storage platforms. So you can utilize the same commands and such that you would use. If you can basically just treat it as if it was an AWS endpoint. We also have, it's not shown here because I am hitting AWS S3 here, but we do also have the ability to set an S3 endpoint that allows you to specify that custom endpoint if some other cloud storage provider happens to have a different endpoint that they need you to use.
Thank you.
Cool. Let's see here. I want to go to this. Oh yeah, so what I want to point out here is that as this is running, oh, it started. Okay, cool. So we should be able to see this different now. Okay, so this is kind of cool. You can see that right here, this job was pending. And if I go to Fuzzball provision resource list, which gives us the list of all of the compute resources that are currently running on the cluster, you'll see that we have 4 of these creating. Now, I won't make the more verbose output come out of this, just because I'm not sure if I want to have that shown here. But if we were to look at the more verbose output from this, we'd be able to see that these are running P3.2 2x larges for each one of these. And you'll notice that when it was pending, these were creating. When it was started, these are running. And so that shows that this job is now running. These are the resources that it's running on. I don't think it uses the GPU for every bit of the computation. So if this doesn't show an incredible amount of usage, that'll be why. But if we were to do something like Fuzzball workflow exec,
real quick, if you don't mind me jumping in real quick, I have a slide I can share real quick that'll kind of graphically describe what it is that we're seeing with regards to the data ingress and egress and whatnot. So
cool.
here,
that sounds good.
I'm going to share this slide real quick.
Yeah.
So what this is demonstrating is on the left side, you'll see the user's workflow coming into Fuzzball Orchestrate. That workflow is what Forrest was describing. It has within that, it has the context of ingress, it has the context of the job pipeline, and then the context of the egress. That comes into Fuzzball Orchestrate. Now, Forrest is running this up in the cloud right now. So when that workflow comes in, it's going to start doing a bunch of things kind of simultaneously. You can see some of these things depicted on the right side. So for example, you can see the data lake. The data lake in this case could be, any form of an S3 data store, could be HTTP endpoint, it could be anything. We're going to ingress all of the bits of data we need for this job. You're going to see the ingress that was under the volumes in that. You're going to see the containers coming in from that as well. And then we're going to set up the volumes underneath that. Now, in parallel to that, because we're running this up in the cloud, Fuzzball is going to be provisioning resources, cloud resources, instances to actually run that job pipeline. And it will satisfy all of the hardware requirements of that workflow in order to basically run that job. So if you're running an MPI job, if you're running task arrays, if you need GPUs, it will actually provision that resource out and compose that resource as well if you need, and if you have composable hardware. Once that is done, it'll start running that job pipeline on top of this volume. And then at the very end, we're going to do that egress. So what you saw Forrest sharing was a lot of these pieces being depicted by the monitor, basically by what is actually running it. And you can follow these different steps. So I'm going to actually go back. Let's go back to Forrest's screen now. And he can actually show exactly what that is and what stage it's in. You're still muted.
You're on mute, Forrest.
Thank you.
There you
go. So as I as I kind of pointed out here, we have all of these GPU nodes running. If I go ahead and do a Fuzzball workflow exec, and then I provide the name of the workflow, the job that the workflow is running, and then an arbitrary command. If I were to specify TTY here, I could do /bin bash and get a shell into this. I'm just running NVIDIA SMI though, in this case. You'll see that we actually have the output from NVIDIA SMI coming from one of these compute nodes. You'll see that at the moment, we don't have any utilization. Like I said, it's not going to use the GPU for every part of it, so we don't expect that. But we do have processes running there. And then we do have some amount of memory that is being used. And if we go down here, we can see we have 4%, so not much, but starting to use the GPU and that memory changing. And so you can kind of see there that we have some GPUs that we're running on here. I'll move back to the status of the workflow, and we'll see where that's at. You can see it's still on this run QMCPACK step. Why don't we just follow the logs for a second and see what this is outputting. There we go. We can see that we get this pending message when there's nothing being printed to the log at the moment. But we can see so far what's been run as a part of this simulation. So basically just a lot of info here. I'm trying to find the line that references GPUs. Yeah, here we go. Total number of MPI groups 1, 16 ranks. Ranks per node 4, accelerators per node 1. So we see that we have 1 GPU per node there. There's another, I think, bit that says something about CUDA, but I'm not seeing it right off the top of my head. But anyway, you can see that we're finding accelerators and stuff there. We just get a memory usage report from it as it runs. Then yeah, we'll, like I said, get this pending message. Might want to stifle that a little bit, make a note. But yeah, so we can see that this is running. This will take another few minutes to run. So if we wanted to, we could actually start something else up right now and kind of go through that.
Cool. Yeah, go for it. Sounds great.
Alrighty. I'm going to hop out of this and I'm going to hop over to my Dask example really quickly. So like I said, this is a little bit of kind of a basic example. This just basically shows Dask running in general within this platform, and kind of how more of the purpose here is to show how a task array works and how it can allow you to process many input files at once in an embarrassingly parallel manner. So we have this workflow here. Sorry, I'm looking at how big it is on the actual screen. Should be good. So we have this workflow here. We're going to, once again, reach out to my S3 bucket and pull down moredates.targz. Moredates.targz has 100 input file, or it has 100 input folders in it, each one of them kind of looking like it's got a random date basically attached to it. And inside of each one of those is a file, prices.txt, that has 20,000 random numbers in it between 50 and 100. So we'll bring that down, and that'll get pulled into this data volume that we have here, V1. This is an ephemeral volume, so once again, this will last for the lifetime of the workflow, but then be destroyed once the workflow is done. So we'll pull down this bit of data from that S3 bucket. We'll basically just do a similar untar job to what we did before. I'm using, just kind of notably here, a private Docker hub registry, by one that I get. I'm using a private Docker registry here to pull this down. So just showing you how you can pull down from directly a private repo on the Docker hub itself. And you can see I have an access token there configured within our secret system and stuff like that to be able to get in. So I'm pulling down this Dask compute image that I made. This basically just includes Dask and some other components. Once that's pulled down and is untarred, we're going to pre-process the data. So we'll use this little script right here called mungefolders.py. There's a few different ways you can do this. This is kind of a Pythonic way. When we have a task array, the interface that we get into being able to assign different parts of that task array to, or assign the resources that task array is bringing up to different subtasks of the overall computational job we're trying to run, is through this FB task ID variable here. So we essentially get, depending upon what the task number here is in this task array, and I'll explain these a little bit more. I'm kind of getting a little ahead of myself explaining, because I have to explain this script right here. But this FB task ID is set with the number that this, the task number that it is relative to what's set here in this task array. So essentially what mungefolders does is it goes through the 100 input files that we have and appends to the front of each one just a running count from 1 to 99, so that that file, or so that the task array can then have a way to pull down and link a specific input file to a specific computational resource that's brought up. So this is basically just going to take that dates file, munge it a little bit, add those numbers to the front of it. And then once that's done, and you can see we're using very minimal resources for that. That's a really quick task. We then get to the last one, which is run Dask. And like I mentioned, this is a task array. I don't think that we've shown one of these before, so I'll elaborate a little. A task array enables what's called the embarrassingly parallel model of high-performance computing. We've gone over NPI quite a bit, which is actual core-to-core and node-to-node communication happening in a high-performance computing parallelized simulation. Embarrassingly parallel is essentially the case where, in contrast to MPI, where incredible effort is required to write an MPI application, with the embarrassingly parallel model, little to no effort is necessary in order to separate the input into discrete computational tasks that can then be run independent of any other task. So in this case, we have 100 input files. We're going to start, I might be having off by one error here, but I'm going to ignore that and say it's 100. So I have 100 input files here. I will start numbering them at task 1. I'll stop numbering them at task 99, and I'll run 10 of them at once. So what we're going to see this do is bring up 10 nodes at once to run this. And then this is going to basically do this processing right here in this Dask compute file. You can see that we are essentially opening that prices.txt file, reading everything in from it, and then feeding everything that we had in it. is this? One moment. There we go. Sorry, I've confused myself once or twice with that. This is the one that yeah, sorry, this is the one that we're looking at. The other one there is kind of the working copy. This is the one that we're actually running in that, which will make like this make a little bit more sense here because that's covers a corner case in it. Anyway, so we're, like I said, this is essentially going to take those 20,000 input numbers from those 100 input files, do essentially raising each one of them in those lists to the power of 2. It's going to sum every one of those 20,000 now raised to the power of 2 numbers together, and then divide that average by 20,000, or divide that number by 20,000. So we essentially get, just average plus num 20,000. Yeah, so we get the average more or less of what those 20,000 numbers is in there. Sorry, can't math on the webinar for some reason. But yeah, so that's what this will do. Moving back to this task array over here, with those 100 input files, yeah, it'll map to that. We can see that Python 3 runs, and then in this file, we take in the first member of the arguments array. And so that's why we pass it to it right there. So you can see how we link the task array into some actual code in this case. I'm going to go ahead and run this. And in the meantime, we'll return also to QMCPACK because it looks like it is doing something. So we'll head back over here real quick. So you can see QMCPACK is still working. The run QMCPACK step is finished. The ls step is finished, and the outputs are actively being tarred. So once that's done, this egress will continue. And in the meantime, let's just open this up real quick. So yeah, we can see here, QMCPACK execution completed successfully from the run QMCPACK job. And you can see here, tar outputs, we're gradually getting an output of what's being tarred in that directory. And that we'll have on S3 in just a little bit. Let's go ahead and start Dask before we run out of time. Let's see here. It's Dask demo number task. Wait, where's that? Oh, sorry, I was conflating the path and stuff there. There we go. Dask / numbers / number task. Right. Yeah. And you can see some other stuff in here that's essentially just testing other just scripts, stuff like that, just kind of the mess from getting this working that I forgot to clean up. We'll go ahead and watch this status for a moment because this will be kind of fun to watch unroll. So this workflow has started. We've got this S3 ingress happening right now. So we're bringing in that more dates.tar.gz file from S3. We've already got the image cached, basically, because I've been running this. And in here in just a moment, we'll start to see these jobs kick off. We'll watch this here for just a moment. I might keep an eye on that. Let's see. When the task array kicks up, it'll essentially unroll 10 tasks out of it, and this output will become much more kind of complex. And I want to make sure that we capture that here. So once we see that, we'll kind of let this run for a second, and I think we are going to pivot really quickly to Quantum ESPRESSO because that takes about 15 minutes to run, and I see that it's 11:30.
I'm simple-minded. I love to see the output actually changing as it's going through the different tasks and watching it. Mm-hmm. Something started, something finishes, something is happening over here now, and you can actually see all of the dependencies of the job graph being resolved in real time and implemented in real time as you watch this output. It's super cool.
Yeah, exactly. So as you've seen here, this this job up here, run Dask, has started, and it's unrolled 10 tasks out of it. This has started this kind of top level job for this task array because at the moment it's spooling 10 nodes to run these on. So these are all pending. We'll kind of start to see those come up here within the next couple of minutes or so. I'll go do a Fuzzball provision resource list so we can maybe.
Is it possible?
See a big old bunch of them going.
Oh, that is super cool.
4,
Is
5,
it
6,
possible
7, 8,
to kind
9,
of
10,
pre-spool? is it possible to pre-spool or pre-provision some of these resources if you know that you're going to have some resources that you're going to want to run so the cluster is ready for it?
Yeah, we just do Fuzzball provision resource create. And then I think we would just do something like users/fbert@ciq.co /default CPU definition. Is that what it's called? Default CPU node. Yeah, there we go. Okay. Yeah, so that spooled up a resource. So that if we were to kind of look closer at this, and this is a bit of a mess at the moment. I think that there's a few different workflows conflating here. So that's why we see some are running, some are creating. I suspect most of the ones creating are the 10 going for this, which actually let's return to before I forget about that. Yeah, okay, so those are still spooling. So yeah, we're just kind of waiting a couple minutes for those to come up.
Sorry for throwing you off on that.
Oh no, it's fine. That's totally fine. It's a good point. That yeah, you can pre-provision those. I'm not sure how sophisticated at the moment the linking of those created resources is. Like whether or not it'll still want to provision some. I'd have to kind of investigate a little more. But oh, there we go. Okay, cool. We see this starting.
And if this was a physical cluster that was on-prem and all the resources and nodes are already there, there's no spooling up. All this happens instantly, right?
Mm-hmm. Yep, exactly. Because the resources are already there. It's not having to do any negotiation with the public cloud provider, anything like that to bring these up with whatever, playbooks, whatever like that. It's So we see these starting here. These are this will start to like finish these tasks. Yeah, there we go. And then we'll start to see more starting. That concurrency, in case I didn't make it clear, that concurrency one means that we'll have 10 nodes running at once. So we'll have 10 Dask tasks maximum running at one time. And so we can see we have at the moment 1, 2, 3, 4, 5, 6, 7, as we're waiting for a couple more nodes to spool, I think.
And it looks like it's reusing those nodes. So nodes that have already spooled up and been provisioned, it's not shutting those down and then restarting them. So we're actually seeing them come back up much faster now.
In this case, yeah, I want to point out that there are nuances to that depending upon where you're looking. But in the case of a task array, yes, it will just continually land those tasks on the resources it's already done, which you can see the usefulness of if, the instance you're trying to use is, $30 an instance or whatever, just throwing a number out there. You wouldn't want to have to spin up 30 or 100 $30 instances. You just want to do 10 of them and then have it run. So we can see that this is going to go through and process those files pretty handily. We can go ahead and take a look at the log output as this goes. Like I mentioned, this is just going to print the average of those numbers. And because they were all generated from about the same random space, we should see that the numbers being printed out will all be within some small amount of each other. So we'll just go ahead and do this. And yeah, so what we see here is all of these tasks gradually printing out their outputs as they go. We can see the task name right there. We sometimes get these heartbeat ones failed, but if you look, we've got one on task 22, but then task 22 completes successfully right there, so we're not worried about those. You can see that we're essentially just printing out what the name of the file that we derived this data here from was. So in this case, this is meant to represent January 30th, 1999. But in this case, we assigned this to task 4, so we munged this little 4- here at the front just to make sure that we could map that to a task. So if we come down to the bottom, we see that this is still running and still moving. I'm going to give me just one moment. I'm going to check the resource counts to see, or a little closer to see if everything is cleaned up. Let's see here. Whoops. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. Yeah, I think we're good. I will go ahead and...
Again, while Forrest is bringing that up, if you have any questions, please start entering those into the chat so we can answer those as we go.
Absolutely. So yeah, I'm gonna, while that finishes up, I think it's fairly apparent what's going on there. I'm gonna move over really quickly and show the Quantum ESPRESSO workflow because that's kind of cool, and we still need to show some of the AWS stuff. And I know we're starting to run up on time. So this one right here, QEspresso data volume, QMCPACK egress directory. Did I accidentally paste it on this one as well? QE outputs, AU surf. Oh no, that's an egress, sorry. I was thinking over here of egress directory, so I was reading egress as its own volume, and I was like, why do I have 2 volumes set up on this one? No, this is 1 volume, okay. So in this QEspresso workflow, you can see that we have 1 volume we're creating here, QEspresso data volume. We're gonna bring down, once again, some data from that S3 bucket, just these QE inputs. The inputs for QMCPACK and Quantum ESPRESSO in this case are basically just available out there. I believe that they're the examples that are on the NVIDIA NGC if you visit the container pages for these pieces of software there. So you can see we're going to do an ingress. So we'll bring that bit of data in here. And then once that data is done, we'll egress that out to this S3 bucket once again. You can see we have 1, 2, 3 jobs in this case. The first one is an untar, not like anything we haven't seen before. So that's pretty simple. Just going to untar that data. The second job here is going to do the same thing resource-wise that QMCPACK just did. It's going to bring up 4 nodes with the OpenMPI implementation of the MPI wrapper, looking for 4 cores, 60 GB of memory, and 1 GPU on each one of those nodes. So in total, we'll have 4 V100s coming up. You can see that we are making our CWD, the inputs file that we untarred in the prior step. And then we're just running just the QMCPACK executable here over that input data. There's 2 files that get unpacked from that. This tarball right here. Whoops, let's do that again. And so yeah, and then you can see the image we're pulling down from the NGC. There's not much else to see on that one, I don't think. And then up here at the top, we once again tar up the outputs, and then we place those into that data directory that we have so that we can egress those out to S3 afterward. We'll also notice we have requires here, run QEspresso, untar. So we're creating a basic directed acyclic graph there for this to follow. We'll move over really quickly to the command line once again, and then we'll go ahead and run that one. So we'll go ahead and do, sorry, like I said, I looked to some things I don't quite want on camera. And so we'll go ahead and find where I put, there we go.
While you're typing that, we do have one question for you, Forrest or Michael.
What's up?
What does the workflow do if a node fails during the run?
So if a node fails during the run, it depends upon what the behavior you defined in your workflow is. We have an ability to set policy on a workflow job. And so you can set 2 types of policies, a timeout policy and a retry policy. A timeout sets how long the, I need to make sure I start this. There we go. A timeout policy defines how long the workflow job should be allowed to run for before it gets terminated due to timeout. And then retry will tell you how many times a job should retry if it fails for any reason. And so that's just as simple as adding that policy retry to your workflow.
So pretty simple. Just add a line and it'll try. Retry.
Yeah, I'm looking for workflow that has it on it, but I can't find
I cut
one
you
right
off,
off
Michael.
the top of my.
Sorry.
Cool. Really quickly, just to link what we're doing here to what that definition we just looked at is. You can see that, once again, we have the workflow up here, start and finish time of the workflow, the 1 data volume that we created in that workflow definition. We have the file ingress that we did, so that's already finished. We have the file egress that we're going to do, which is pending because these jobs haven't finished. We have the untar. We have 1 image that we're using, just Quantum ESPRESSO in this case. And then we have untar here. Like I said, finished. And then we're just waiting on Quantum ESPRESSO now. So this will take, similar to QMCPACK, a few minutes to spool up those nodes. But speaking of which, in the meantime, let's hop back over to QMCPACK and see what it's done in the meantime. If I can find where that status is. There we go. It's finished, including our egress and everything. And so if I just hop on to a little AWS S3 LS and do, let's see here, S3 Vert storage. We can see 1128, 428, so just about 10 minutes ago or so, QMCPACK results full tar.gz. And AWS S3CP, let's see here. Put that there. See this to the current directory, right? Yeah, cool, there we go. All right, we'll give this a moment to download. And then I'm just gonna tar-xf that and just to show the results that we have in there. I don't have any fun graphs or anything that I can bring up and show with it, but we should be able to see fairly easily what the output files here are and how we've just recovered those.
You're just showing off what a reasonable internet connection looks like.
That was amazing.
Yeah, I definitely awesome. I like my 1 gigabit down. They tell me that the local fiber place can get me 1 gigabit up, which is very useful for container pushes. So I'm exploring that as well.
I'm not going to tell you what mine is where I'm currently at. Sometimes I get 20.
Screaming.
I know.
Let's see here.
Another question. So how do NUMA architectures interact with the workflow? And are there some examples?
Yeah, give me just 1 second to, what screen do I have up? Oh, I've got this one. Okay, good. Give me just 1 second to get into these. Ooh, what's it called? Just 1 second. What is that on our tart up? Host PWD. Okay. There we go. Okay. Because that tarred up the host PWD directory, that's what it unfortunately gets decompressed as. But if we go in here, you can see that we have all the files that we just wanted to recover from it. Our initial data files that we brought in still tar-gz'd, so we may want to avoid doing that if those are significant because we wouldn't want to just be copying those over. But anyway, we have all of the kind of information that we provided to this. We have, I believe this is the actual input file itself. And then we have all these scalar.dat files that represent the outputs. I don't have a little QMCA demo spooled up to actually pull, like I said, some graphs or something out of this. But you can see those are the results. And if we go do something like, sorry, I'm going to find, there we go. And if we go to this and we print out all the logs, once again, as I showed earlier, we can scroll back through this. We've got, device memory allocated via the CUDA allocator. So talking about, allocating GPU memory. We've got the LS here that we ran. So that's just showing us kind of what's in that data directory that we ended up tarring up and bringing down. But I'm trying to see. It might be Quantum ESPRESSO's output that has a very obvious point where it says using CUDA accelerated MPI or something like that. Oh, here we go, running on an NVIDIA GPU via CUDA acceleration. That's useful. Okay. So yeah, so that's QMCPACK. You can see, once again, execution completed successfully. We have our timing and information like that here at the output. Really quickly, while Quantum ESPRESSO is probably still working, we'll hop back over to Dask just to finish that out and show what that looks like. So we can see in this output, we have the single run Dask and then 100 or, 99 tasks coming off of that. All of them starting and finishing, 128. Well, that's the whole job itself, I guess. So we expect that to take a few minutes. All of these finishing fairly quickly, 11:31:15, 11:31:48. And you can see how, as we progressed through all of these input files over the course of 7 minutes or so, we processed all 100 of them. And so if I go do a log-f, we can extract all that data out of it. And once again, like I noted, we get this odd error sometimes, but we ultimately still get results. And as I mentioned, you'll notice these are all somewhere in the vicinity of 5,800 and about 40. Like I mentioned, all the random numbers here were generated from the same between 50 and 100. So we expect to see about the same thing on each one of those, which is good that we do. So that's Dask and QMCPACK. Let's move back to Quantum ESPRESSO and see how it's doing. We can see it's running right now. Why don't we just take a look at that while it goes? There we go. Once again, we still get that pending message. We'll have to note that that should be stifled when there's, so it's not just constantly printing. But we can see that we're starting to get some output here. I imagine we'll get some more here in a second. But if we look through this, there, like I mentioned, GPU acceleration is active, GPU aware NPI enabled. And then we can go and we can see 16 NPI processes, 4 threads per NPI processes distributed on 4 nodes. And then we can just get information about the simulation. We can see that this is printing, except for when it's pending. I think this does 20 iterations, and it's on iteration 1. So that will take a little bit to run. So we'll move back over to the status. And what else do I want to do? Take a look at this. So yeah, you can see that at the moment we only have 5 nodes running compared to the very large amount that we had earlier. So all of those nodes that we spooled up for Dask, all the nodes that we spooled up for QMCPACK, all of those have been spun down, and they're obviously no longer visible here in our resource list. We have 5. We expect 4 for this run Quantum ESPRESSO one, but it's probably just something taking a little bit to spin down, so I'm sure it'll disappear here in a moment. But yeah, so that's Quantum ESPRESSO. Like I said, this will take probably about 12 minutes or so to run. And so once that's done, really quickly, even though we're at time, I think we should hop over and take a look at that S3 bucket and show how those results have been uploaded there as well.
And real quick, maybe I missed it. Did we address the NUMA question?
Oh, no, we didn't. Thank you for the reminder.
You got it.
The NUMA question, let's hop back over really quickly. I'm going to bring up my text editor because that's the easiest spot. So just to pick a random one of these, we'll use the run QMCPACK job because it's the one that we're most likely to actually have some use for a NUMA node on. You'll notice that when we set the CPU cores that we want here and whether or not we want hyperthreads to be present or enabled, you'll notice that we can set a NUMA affinity here. This affinity can do, there's 2 other possible affinities. I can never remember the name of the one that's for the whole node, but I believe they are NUMA, socket, and core at the moment. And so core is the most coarse. Let me back up. The affinity that we're looking at here is where we're going to choose the CPU cores on this node from. So obviously, if we have 32 cores on a node, depending upon what's going on with the server, we may want to land all of the cores that we're using within a certain subset of the total amount of cores on the node available. This is typically done when we have what's called a non-uniform memory architecture underlying in the server, like the compute node. And NUMA is essentially where, say you have a 32-core machine, you have 200 gigabytes of memory on that node. If you have 4 NUMA nodes, you would probably have something like 8 cores to a NUMA node, each one of them with 50 gigabytes of that memory that they can access fundamentally faster than any other cores in that system can. And so a NUMA architecture, being NUMA aware in your simulations is a really easy way to instantly add efficiency because, say we only need 8 cores of that 32, it becomes highly advantageous to land all of those cores on the same NUMA node so they can all have a space in memory that they can access faster than any other core. And so that's the NUMA affinity. In this case, with 4 cores, I don't think it's going to be too important. We're not undersubscribing this compute node. We're using all the cores available on it. So by default, kind of our affinity isn't really too important there. But you can see how if we were doing like a subset of a node or something along that type of thing, NUMA would be immediately, or that affinity there would be immediately a way to add efficiency to your simulation with just a couple types on the keyboard. As I noted, there are 2 other possible affinities, socket and core. Socket basically just minimizes the cores to the number of sockets. So, if you've got a compute node that has 2 16-core CPUs in it, and you specified that you wanted 16 cores, and with the socket affinity, it would land all of those cores on 1 socket. So that, once again, if you're looking for socket-based affinity, that's how you do that. And then core basically is like I said, most coarse, and it just basically just picks from anywhere on the node. So that's how we do NUMA awareness. Just another kind of interesting similar option is by core. And by core allows us to specify whether or not we want the amount of memory that we tell it to go and look for to be for each core. So in this case, we're saying false because we don't want to need 240 GB bytes in total, 60 times 4. So we say by core false, and so we're only looking for 60 for all 4 cores in total. I'm going to switch this, and we're going to take a look back on the command line and see what's what. Still running. Like I mentioned, this will take a few minutes, but let's kind of see what this is doing right now. It actually looks like it's finishing. Cool. Yeah, so these are just like random ending warnings that I presume happened because this is literally written in Fortran 90. So I'm sure we're going to get some interesting input out of anything written in Fortran 90. As I noted earlier, when we look through these results that we have here, we can see that it is very obvious that we're running on 4 nodes. It's very obvious that we're using some type of GPU acceleration. We can see we have 56 atoms here of gold that we are simulating in this case. If I read all of this correctly, you'll see that we get kind of some little bit of information here. This is the amount of RAM that we'll need. So one of the reasons why we're using, well, this is a little scaled down from the example, but it doesn't matter. We can see that we did 20 iterations. So 1, 2, 3, 4, 5, 6, blah, blah, blah. Or we did 13, actually. Oh, we did 13, actually. Sorry. My test runs did 20. Maybe I changed something. But you can see we get, yeah, all the numbers that we expect, all the output. We have a note here that says we have a output data file being written that we're going to push to S3 in just a second. You'll see we have job done. This run was terminated at this time. We get CPU and wall clock there. And then we also get GPU time. So we can see, I guess we do only get CPU on that. So we see we get wall clock and GPU time printed out there. And then we're just getting the kind of tarring up of the outputs here at the moment before those will be uploaded. So once tar output's finished, we'll see that data egress start. And then just like we did before, I'll hop back over to kind of just AWS S3, LS, and I will show that there. And also while I'm at it, let me bring up my AWS console so that I can just show the bucket view there as well. S3. Okay, cool. So yeah, while we're waiting for that, here's my, oops, I've lost the StreamYard in my tabs. There we go. So let's see. There we go. Sure there's nothing I don't want to reveal here. Yeah, we should be good. Okay. There we go. Can everyone see that? Okay. This is just the AWS bucket interface. You can see that I'm here on my BERT storage bucket that I've been referring to this whole time. You can see we have more dates.tar.gz, which is the quantitative finance data that we pulled in. You can see we have S32 example.tar.gz, which is what we pulled in for QMCPACK. And you see we have QE inputs.tar.gz, which is what we pulled in for Quantum ESPRESSO to use as an input. And then we have QMCPACK results full tar.gz here, which is the QMCPACK results that we just uploaded. It looks like the Quantum ESPRESSO workflow is just finished in the background. So actually, if I refresh this, boom, there we go. QE outputs ausurf.tar.gz, which is exactly what we expected there. And then if I go back over to the command line, you'll see that this workflow is finished. The data egress finished there while we were looking at that bucket view. And then, much like I did before, I will do, let's see here. I am just going to make a quick little temporary directory to move this into, just to make sure I don't conflict with anything.
So it's just showing off your internet speed again.
Yeah, here we go. Let's see, grab this.
We don't have enough time on a webinar for me to download stuff like that.
I'm going to pull 2 gigabytes here in just a moment. So in just a moment, we'll have that coming on out. It might take a little bit to untar, but we'll be able to look at those results here in just a moment.
John, look at that.
So let's do this. And then we'll just wait a second for that to run. So that's about what I had as far as demos. Yeah, that's about what I had.
Excellent. Well, thank you very much for us. I know
go.
you put in a lot of time getting this together for us.
It's very cool to get to show off. So you can see here now, we can go into this QE inputs file. Like I said, the thing is a little rough here. I'm not really concerned about not preserving what the volume looked like when it was attached to it. But you can see if we go in here, we continue to go down these directories, we have our output files there. So that is everything I had. Yeah,
fantastic.
That's everything I had. So,
well, thank you very much, Forrest, for that. Michael, I don't know if you were, oh, we lost Michael. There, he's back. Michael, Greg, I don't know if you guys have anything you want to add before we close.
Sorry to interrupt you, Zane. I just wanted to say that was super awesome for us. You put a lot of work into that, we can tell, and it really demonstrates the use cases of what it is that Fuzzball and more generally an HPC 2.0 cloud native, federated computing platform, how it can actually work, how it can actually help users, help researchers, and whatnot. I think you did a great job demonstrating that. So thank you so much.
Thank you. And if I can just one more time share my screen, I've decided to gonna show this really quickly. I can't show this live just because there will more than likely be issues on the public cloud provider's side with having enough of these available. A problem with their capacity, not anything to do with our system. But if I run this right here, this is something that I ran yesterday. We've featured lamps examples on here. We had kind of our most advanced one yet yesterday. And so we can see, and I'll pull the workflow off of this in just a moment as well, but we can see that this run I did yesterday, like I mentioned, they don't always have capacity in these instances, so it was a bit of a crapshoot getting it running, so I only have results here. But we can see that we have this 4x2x4 NPI processor grid, that we are using up to 4 GPUs per node. This is running on, this is also running an NPI, as we can kind of see due to the timing loss and communication here. And then also through the workflow. And so just wanted to show, we've done a lot of single GPU node examples thus far, but just wanted to make sure I point out we have no problem running across nodes that have multiple GPUs as well on them. And so these results you're looking at here were generated from a run of lamps that was done over 2 nodes at once with 4 GPUs on each node. And so in total, the results that we see right here are generated from a run of lamps that's running over 8 V100 GPUs at once across 2 nodes on this public cloud provider. So like I said, I can't easily demo that live, but I did want to share those results because it did work at least once. They were able to issue me one of those, so it did work. So yeah, this is multi-GPU.
We've seen this now several times where we're trying to provision resources up in the cloud. And I know that the idea of the cloud is you have an infinite number of resources whenever you need them available. Yeah, we're actually not seeing that. Depending on what availability region we're on, what cloud we're on, because we're testing on all the major clouds at this point, we're getting kind of mixed feedback regarding where can we actually spin up big resources, big jobs. And yeah, we've hit the top of capacity now a number of times up in the cloud and whatnot. And this is one of the reasons why it's so incredibly important to have a multi-availability zone, multi-cloud solution, such that you can find where those resources exist and bring your job to those resources. Because if you're just running in one, you're probably going to hit scalability issues because the cloud is not actually infinite, especially when we're doing really kind of hardcore compute focused jobs. So being able to distribute that as wide as you can possibly distribute that, find the best prices, the best resources that you need, match that up, and automatically have that job run in the right location. It's kind of a big deal.
Absolutely.
Awesome. Well, yes, thank you everyone for joining and for tuning into the webinar. Like I said, or like everyone kind of touched on, like I said, it was fun to put all this together and to get to show it off. So I hope it kind of pushed the envelope for what we've shown Fuzzball can do. So very cool.
It's great. Thank you very much. And guys, we always ask that you like and subscribe so you can stay in touch with us and we can keep putting out things for you to watch and ask us questions on. We appreciate it, and we will see you again next week. Thanks, guys.
Goodbye, everyone.